Hi everyone, my name is Anlan Zhang, and today I'm going to present our paper, Habitus, Boosting Mobile Immersive Content Delivery through Full Body Pose Tracking and Multipath Networking. It is a joint work with my collaborators, Chendong, Yuming, Ahmad, Zejun, Feng, and Shichang. So to begin with, immersive content is everywhere. We have these 360-degree videos, the VR games, and the emergent volumetric content, which are typically represented by 3D point clouds or 3D meshes. This content provides the viewers immersive experience by allowing them to exercise 3 degrees of freedom to 6 degrees of freedom motions when watching the video. However, they are also very bandwidth intensive, and it's very difficult to deliver high quality immersive content through common wireless links. And the good thing is that our wireless communication technology is also evolving. So we have these omnidirectional radios, like 4G LTE, low band, mid band, 5G, and the AO 2.11 families. And we also have these mmWave radios, like the mmWave 5G, which has been popular in recent years. And we also have these AO2.11AD and AO2.11AY in the future. So compared to the omnidirectional radio, the mmWave radio provides much higher bandwidth, which makes it promising for streaming bandwidth-hungry immersive content. But meanwhile, the signal strength of mmWave also attenuates much faster and is more vulnerable to blockage. So we did a case study to see if we can simply using mmWave for volumetric video streaming. So in this simple personal office, we set up 2 access points, one for AO2.11AC and the other for AO2.11AD. And we also set up a content edge on the room. And then we let the user wear a headset, and we mount a smartphone on top of the headset that can accept both AC and AD signals. And we play our test application, Vivo, which is a volumetric video streaming application published in MobiCon 20. And at the same time, we let the user follow the walking trajectory shown in this figure to move in the room. And we repeat our experiments twice. The first time we use AC for streaming, and the second time we use AD. And our observation is that using mmWave does help improve the video quality. But however, we find that the video stall is also drastically increased. And the reason is that mmWave throughput is highly fluctuating when the user is under constant motion. Here we show the spatial heat map of both AC and AD throughput when the viewer is moving. And it's easy to see that in some positions, the mmWave signal is quite low due to the human body blockage. Actually, there have been some systems working on using mmWave for streaming. However, these systems are either requires specialized hardware or require modification on commodity wireless infrastructures, and or they are still struggling with the frequent non-line of sight situations. So we think that we need a robust and easy to deploy solution. So to this end, our solution is a system called Habitus. It has 2 core designs. The first one is multipath networking. So remember, we not only have the mmWave radio, but also we have the omnidirectional radio, which is much more stable. So the first design of Habitus is using both these 2 heterogeneous links for content delivery, and use the omnidirectional radio as a base link to provide a base viewing experience to the viewer, and opportunistically use mmWave when possible. And the second design of Habitus is about how to use the mmWave. So our design is actively predicting the future mmWave throughput, and let the multipath scheduler and also the application make better decisions. So we face several challenges when building our systems. The first one is how to predict mmWave throughput accurately especially when the viewer is under constant motion. And the second one is, since we are using machine learning-based prediction models, and the model needs to be trained offline, but in an online use case, there will always be some unseen changes to the model. So how can we adapt our model to these unseen changes? And the last one is how can we do multipath scheduling over the heterogeneous links? So I will begin with the throughput prediction part. So here I show a very simple throughput prediction model that takes the historical network measurements as its input and predicts the future network conditions. And remember, we have this spatial heat map of millimeter wave throughput in our case study. And the insight is that the millimeter wave throughput is highly correlated with 6 degree of freedom head motions. So a straightforward improvement to the model is adding the historical 6 DOF head motion as an additional feature. And this has also been validated by some previous studies. And we have a further insight here that there is actually spatial correlation among body parts when the viewer is under constant motion. For example, when the hand-holding controller moves, there usually will be a head movement follow-up, and it will further lead to a throughput change. And this spatial correlation among body parts has been explored in some previous research and has also been leveraged in some other tasks like person re-identification. So our intuition is that, by checking full body pose as an addition and use that as an additional feature to the prediction model, we can further improve the prediction accuracy. And in our paper, the full body pose is represented by a set of 3D key points, each corresponding to a body joint. So to evaluate how much benefit we can get from leveraging full body pose, we first collect some data under some realistic settings. And basically, our data set consists of these 3 features. First, the throughput and the signal strength of both AC and AD. And second, the 6 DOF motion of the viewer's head. And third, the full body pose tracked by a stereo camera. And in our experiment, we set the prediction target as the millimeter wave throughput in the next 1 second. We compare a prediction model without and with pose as an additional feature. And for example, we tried this sequence-to-sequence learning-based model, which use LSTM encoder and decoder-based architecture. And we find that by using pose as an additional feature, we can reduce the throughput prediction error by 17%. And we also investigated some other machine learning models like gradient boosting decision tree, MLP, and RNN in our paper. And the overall finding is that by using pose as an additional feature, we can reduce the prediction error by 5 to 29%. And however, we are not done yet. As I said before, a practical issue of using an offline pre-trained model at runtime is that there will always be some performance drop. And the reason is that the model cannot adapt to the changes deviating from its training data. For example, in our settings, the location will change, the user may be changed. The user may exercise new motion patterns, and there might be some statical environmental change, like a chair being moved, and there will also be some dynamic environmental change. For example, when work by spectator create a temporal non-line of sight. So to handle these unseen changes, our intuition is that there is actually some fundamental knowledge learned by the machine learning models. For example, the physical property of millimeter wave and the throughput distribution in certain positions at a fixed location. And therefore, the prediction model will have different sensitivities to these changes. For example, the changes that reshape the fundamental knowledge learned by a pre-trained model will have larger impact. For example, in our settings, when the location changes, the throughput distribution of the millimeter wave radio over the space will be largely reshaped. So we envision that will have the largest impact in our settings. So we systematically quantify the model sensitivities to the change. So basically, we use a pre-trained model to predict the data from a new location, a new user, or a new motion pattern. And we also manually create some static environmental change. For example, we put some chairs in the space, and we also manually create some dynamic environmental change. For example, here, we use the Roboticon to periodically inject an aluminum box within the line of sight between the access point and the smartphone. And then we measure the prediction error increase when using a pre-trained model to these changes. And here shows our result. And basically, we believe that this validates our intuition that the change that reshapes the fundamental knowledge, like the spatial throughput distribution, and will have larger impact on the pre-trained model. And based on our measurement result, our strategy for handling the unseen changes is using transfer learning. And the key assumption is, as what I said before, the fundamental knowledge learned by the machine learning model is invariant before and after change. So when a change happens, we can simply collect a small amount of data and tune the source model to let it adapt to the change. And the benefit is that this will be much faster than training a model from scratch and can be even performed online. We have more dedicated designs for handling different changes, but I will just skip the details for the sake of time. And the second design of Habitus is multipath scheduling. As I talked before, we will prioritize using the omnidirectional radio to provide a basic viewing experience to the viewer. And we will opportunistically use mmWave according to our prediction result. And we further design a trend-aware multipath scheduler to decide whether we want to conservatively or aggressively using mmWave based on the future throughput trend of our prediction. And you can find more details in our paper. So now let's integrate all the things together and show you the holistic view of Habitus. So Habitus has two components, the Habitus edge and Habitus client. And most of its logic runs on the edge side, like the multipath scheduler and the prediction model. And when the user is watching the content, the client will keep updating the head movement and network information to the edge. And the edge at the same time will check the full body pose of the viewer and use that to predict the mmWave throughput. And the last part is our offline data collection and the training and online transfer learning modules. And Habitus is a general framework for immersive applications. It keeps informing the application about the predicted mmWave throughput through a callback, and the application can adapt its own adaptation logic just to make sure the data size will not overshoot the network. And we implement our prototype using commodity hardware and software. And we also show that Habitus can be easily integrated into existing systems like Vivo, the system we use in our case study for volumetric video streaming, by changing only a few lines of codes. Now let me quickly show you the evaluation on the benefit of Habitus. So we still use the volumetric video streaming application to demonstrate, and we consider both trace-driven emulation and the real user trials. The left figure shows the result of the trace-driven emulation, and we consider both the average video quality and the video store. And the right figure shows the distribution of the real user ratings. And we begin with this very simple scheme that only use single pass AD without any prediction for streaming. And then we add multipath, but still without any prediction. And the next scheme use multipath plus prediction, but not check the full body pose. And the last one is our full-fledged Habitus, which use multipath and full-body pulse guided throughput prediction. And the result is that Habitus outperforms the baseline models, and using full-body pulse can further boost the QoE. And you can find a more comprehensive evaluation in our paper. So to summarize, today I talk about the challenge of high-quality immersive content delivery over mmWave, and I talk about the design of Habitus, including multipath scheduling, the full-body pulse guided throughput prediction, and how we handle unseen changes. And we also talk about the QoE improvement demonstrated by our trace-driven emulation and the user trial. And we also release our collected data set and the source code for data collection so that you can collect data under your own settings. And yeah, that concludes my talks. Thank you.